So this is homework 3, I believe, the GoldfeldQuandt homework, which is all about heteroscedasticity. That at the heart of it, we are only comparing two variances. So this is a big name for a very small concept. Here's the Gretel output given to us in the exercise. Let me just try to get this in front. Okay, here's the Gretel output. I'm comparing two models, one to the left and one to the right. Why? Because on the left I seem to have a large variance or standard deviation of the residuals. By that I mean that this range here seems much larger than the standard deviation of the variation of the residuals on the right side. So model 1 is all about the left, this is model 1, and model 2 is on the right. Okay, and number 1, clearly this is a violation of the homoscedasticity assumption. The variance of the residuals does not seem to be independent of x or constant with regard to x. So the problem number 2, we have a null hypothesis. Someone claims that no, the two variances left and right are equal after all. Now, when would we reject this? When the observed variances are too different. So the test statistic has two forms. The first one is probably simpler. We take the ratio of the observed variance, sigma 1 squared, over sigma 2 squared. So that's pretty straightforward. If that ratio deviates from 1 too much, we would reject H0 because then they appear to be too different. Now, we should all know that sigma 1 hat is simply, the variance, what is this? This would be simply the residual sums of squared as any variance. It's just divided by the degrees of freedom. So that is equal to this. And why is that useful? Because sigma 1 is not given in the output, but we do have the RSSs. Where do they hide? So RSS1 is hiding in here, sum of the squared residuals. Yes, this happens to be in German, I apologize. But we've seen this output in English so often that I thought it would be possible to transfer that knowledge. So there you go. I have the 1306 up there, which is here again. Yeah. RSS1 in the numerator and 18.79 in the denominator. So all that is just plugging in. And now I need to divide by the degrees of freedom. And that will be 50 observations on the top. Minus 1 gives me a divided by 49. So divided by 49 in the numerator and divided by 31 because I had 32 observations in the denominator. Now double fractions mean I can simply permute these two numbers and make a product. Okay, so that ratio, now this simple quotient gives me a 44, and with any test, I now have to compare this with the threshold. And what's the threshold? Well, it comes from an F distribution, from an F table. I need 3 ingredients to look up that threshold. The 2 degrees of freedom, which is here, so n1 minus k, and n2 minus k, which is again here, 49 and 31, yeah, and of course my significance level. We said we test at alpha equal to, what did we say? Apparently, even I have to go back here to the problem to see what we're testing. What is alpha? 0.9, so 1 minus alpha over 2 is 0.95, all good. And we need to look this up in either a table. F tables are difficult to find in completion, or we use Gretel as a software. And we find that threshold is to 1.75, so clearly 44 is much larger than 1.75. So we unanimously reject the assumption of homoscedasticity. No way that these two variances can be equal. So that's it for the first part. So number D, which I'm jumping to now, is of a very different nature. So this is problem number D. The claim now is that the overall variance is less than, not the overall variance, so the right part of the variance, the variance of the residuals on the right side is less or equal to a fixed number, and that fixed number we denote as sigma 0 squared. Okay, and I need to look up that number, which is given here. So V is no larger than 20, so that the variance in model 1 is no larger than 20. So the fixed number I was referring to here is equal to 20. What's the test statistic? It's almost easier than before. Instead of taking a ratio of the two observed variances, I only have one observed variance, namely, we are wondering if the ratio of something like sigma 1 squared, actually, sorry, in this case it's sigma 2 squared divided by the claim, yeah, if that's greater than some threshold. Now, the only complication is that I need to multiply by the degrees of freedom, which would be, right, I put the degrees of freedom in front. That's just this test statistic, which obeys the chi-squared law. And now we are in an even better position than before. The product of the degrees of freedom and sigma 2 squared is simply our SS2, which we've looked at before. There it is. So that's 1306 divided by sigma 0 squared, which is 20. And as a test statistic, we get our 65.3185. Now we need a different table. Why do we need a different table? Because when you compare one variance to a fixed value, it is a chi-squared statistic, and there is the chi-squared statistic, which needs two ingredients, degrees of freedom and the significance level. Degrees of freedom is simply the number of, oh, there might be a small mistake in here, I see. No, there's not. 1306, correct. The left model, so I've mixed up right model and left model, I hope you forgive me. So this is all the sigma 1 squared. This is model 1. Model 1, but we are talking concepts anyhow. We should all be able to recover from these little